In this video, we will take a look at our first graph algorithm, depth first search, or more informally DFS. This algorithm is one of the most fundamental algorithms in graph theory, and many of the ideas in this video will carry over to more advanced graph algorithms. For that reason, in this video, I'm going to spend some extra time building intuition for the ideas behind this algorithm. Here's what you can expect to get out of this video. We will first introduce the concept of a graph traversal and what that even means. Then we will try to build our own graph traversal method and show how it intuitively leads to core ideas of depth first search. Once we have an idea behind what depth first search is trying to achieve, we will then spend some time going through the implementation of DFS in a visualized manner. And then we'll finish off this video with some really cool applications of depth first search that I'm sure you're not going to want to miss, so make sure you stick to the end of the video. Let's get started. Given a particular graph, one useful ability involves starting at a single vertex and finding a way to get to every other vertex of the graph. The formal name for this ability is a graph traversal, which is simply defined as an algorithm that visits every vertex of the graph. There are several graph traversal algorithms, and they are primarily differentiated by the order in which they visit vertices. In this video, we will focus on the DFS ordering. So now that we know the basic idea behind a graph traversal, let's take a step back and see if we can sort of invent our own graph traversal. The line of thought that I'm going to present here is actually exactly the DFS algorithm. The goal here is to show you how the DFS algorithm is really a surprisingly intuitive idea, something that with some thought, you probably could have come up with on your own. Let's take a crack at it with this graph. Given a start vertex, we want to find an order that we can go through the vertices of the graph so that we guarantee that we end up visiting every vertex. Let's start with vertex 0. From vertex 0, we have a couple of options for how we might want to continue. The option we choose doesn't really matter too much here, since our hope is that we'll eventually explore all the vertices anyway. Let's say that we choose to visit vertex 1 from here. What now? Well, now that we're at vertex 1, we have a new set of choices for where to go next. It doesn't really make sense for us to go back to vertex 0 since we've already seen it, so let's pick a new vertex to explore. Let's go with vertex 2. And from vertex 2, we only have a couple of options, namely going to vertex 0 or vertex 1. But we've already seen those vertices, right? So what we might naturally do is say, okay, there's nothing further we can do from this vertex, so let's take a step back to where we came from, which is vertex 1. And from vertex 1, we now have two unexplored vertices that we can then go to. Let's go to vertex 3. From vertex 3, our path forward is pretty set in stone. The only unexplored node is vertex 5, so let's go there. From vertex 5, we have a few options on how to continue traversing the graph, and let's go ahead and pick vertex 6. At vertex 6, we've now reached another dead end similar to what happened with vertex 2, so let's retrace our steps back to vertex 5. From vertex 5, let's say we pick vertex 7 as the next node we visit. From vertex 7, the only path forward is to vertex 8, and from there, we again have only one choice leading us to vertex 9. At vertex 9, we've now hit another dead end, so let's go back to vertex 8. Now what's different this time is that from vertex 8, we have already explored everything there is to see, so let's retrace our steps once again. We got to vertex 8 from vertex 7, so let's go back to there. From vertex 7, we have the same story, so we go back to vertex 5. And everything from vertex 5 has been fully explored, so from vertex 5, we now go back to vertex 3, which was the vertex that got us to vertex 5. Same story here, so let's take one more step back to vertex 1. And now that we are back at vertex 1, we have finally found a new undiscovered vertex, so we now visit vertex 4. From vertex 4, there's nothing new to explore, so we go back to vertex 1, which now also has nothing more to explore, which finally leads us back to vertex 0, which now is also completely explored. And now that we're back to where we started, that's how we know we have traversed every vertex of this graph. So I know that was a lot, but the philosophy of how we explored this graph but continuing to explore new vertices as we see them until we hit a dead end is what depth first search is all about. When performing depth first search, think of yourself as a bold and adventurous explorer, where every time you see a new vertex, you will continue to explore new vertices until you hit a dead end, in which case you'll retrace your steps and continue exploration. It's worth noting that there are actually several valid depth first search orderings for this graph. Let's go through one more valid ordering as an example and also as further familiarization and practice with the core idea behind DFS. We can generate another ordering by just changing up the choices of vertices to explore whenever we have a choice while sticking to the core philosophy. Let's start again at vertex 0, but now when we have a choice between choosing vertex 1 or vertex 2 as the next node to explore, let's pick vertex 2. Last time we went through this, if you remember, we picked vertex 1. Again, I want to emphasize that both of these choices are valid, and if you were ever asked for the DFS order on a test or an exam, the instructions must be clear on how to make these choices. A common way to do this is to enforce the constraint that you must always pick the node with the smaller value when you have a choice. In that case, we would have picked vertex 1. Anyways, back to what we were doing after visiting vertex 2, we only have one choice, which is now to go to vertex 1. From there, let's say we now visit vertex 4, which then leads us to a dead end, so we go back to vertex 1. Now the path forward leads us to vertex 3, which then forces us to visit vertex 5, where we now have several choices. Let's pick vertex 8 this time. From there, we'll choose to explore vertex 9, which leads us to a dead end, so we go back to vertex 8. The next vertex we then explore is vertex 7, which leads us to another dead end, so we go back to vertex 8. There's nothing more to explore from vertex 8, so we go back to vertex 5. From vertex 5, we then explore vertex 6, which is the final vertex of the graph that we haven't seen, so that completes another possible DFS ordering. Let's now talk about implementation. It helps to try figure out the implementation on a smaller graph since it has fewer moving parts. Here's one valid DFS ordering for this graph. One thing that you may have noticed about this process through the examples that we've done so far is that it's actually naturally recursive. We start at a particular node, and once we visit that node, it's almost like we can ignore that node in the graph and run DFS on all of the neighbors of that node. So this inspires one initial idea for how we might implement DFS. Given a particular graph G and a starting vertex V, we first visit V. Then for each neighbor of node V, we can run DFS on the graph with that neighbor as the new starting node. Remember that we are representing graphs using adjacency lists, so an operation like finding the neighbors of a node is quite simple. So let's try the first attempt at an implementation and see what happens. We start at vertex 0, and let's say that the first neighbor we end up picking is node 1, so that's the next node we visit. We then go through the neighbors of node 1 and repeat the process. But there's one big issue with this implementation. Take a second to see if you can figure out what the problem is. The issue here is that when we iterate through node 1's neighbors, one of those neighbors is node 0. This means that with this current implementation, we'll end up calling DFS on node 0 once again, which would create an infinite cycle of recursion. So, how can we fix this? Well, what we want to do is ideally only call the DFS function on nodes that we've never seen before. One way to do this is to essentially mark nodes that have already been visited. We can do this by maintaining a list of Boolean values where each one is mapped to a vertex of the graph. Initially, all these values will be false since we haven't visited any vertex. But as soon as we visit a vertex, we can mark the vertex as something we've seen before by changing the respective index to true. Now with the vertices marked appropriately, we can now call DFS recursively on a vertex if that vertex is not currently marked. Let's dig a little bit deeper to verify that this implementation actually works. We first call the DFS function on our graph with starting vertex 0. This will then visit vertex 0, giving us the first vertex of our traversal. After that, we mark the vertex and begin looping through the neighbors of vertex 0. Let's say the first vertex from our neighbors we look at is vertex 1. What happens now is that we make a recursive call to our DFS function with a new starting vertex of 1. The first thing that happens in this recursive call is we visit vertex 1, which becomes the second vertex in our DFS traversal. Now the key idea is that when we look at the neighbors of vertex 1, vertex 0 is already marked, so we can't make another call to vertex 0. So the only remaining option is to recursively call our function on vertex 3. The process is exactly the same. We visit vertex 3, which ends up being the third vertex in our DFS traversal. Now from here, we can go to vertex 2 or we can go to vertex 4, and the choice we make here is arbitrary. Let's say the algorithm picks vertex 4 first. This means that we have another recursive call with the starting vertex now assigned to vertex 4. We then visit vertex 4, which is the 4th vertex in our traversal. Now at this point in the recursion, we now look at all of vertex 4's neighbors, which includes only the vertex 3. But notice that vertex 3 is already marked, so what that means is at this point there's nothing further to do in this call, so we go back to the previous call of the DFS function on the starting vertex 3. We had just finished our call to the neighbor vertex 4, so let's now evaluate the next unmarked neighbor. The only remaining unmarked neighbor is vertex 2, so we can make a recursive call to the function with starting vertex 2. In this recursive call, we visit the vertex, and that becomes the 5th vertex in our traversal. There are no more unmarked neighbors for vertex 2, so we can go back to the call on starting vertex 3. Vertex 3 also has no more unmarked neighbors, so we can go back to the call on vertex 1. Same story here, so we go back to our first initial call on vertex 0, which also has no more unmarked neighbors, which means at this point the DFS traversal is complete. Pretty elegant and simple algorithm overall, and I hope drawing out the recursion gives you a better understanding for why this algorithm works. There's one more implementation of DFS that I think is equally important to understand. This is an iterative implementation where we have the same concept of marked nodes as before, but the key difference now is that we will use a stack data structure to keep track of nodes to visit. So at the start, we will initialize the stack with just the starting vertex, and then while the stack is not empty, we'll pop off the last vertex of the stack. If that vertex has not been visited before, we will visit the vertex and mark it accordingly. Afterwards, we'll iterate through the neighbors of this vertex as we did before and insert them into the stack as long as they haven't been visited before. The best way to understand this implementation of DFS is by seeing it in action. When we call this function on this graph with starting vertex 0, we start off with a stack that contains just vertex 0. We then remove this vertex from the stack, and this is consequently the first vertex that we visit and mark in the graph. As a result, it's the first vertex of our DFS order. Now we iterate through all vertex 0's neighbors, and since none of them have ever been visited before, we add them all to the stack. We then go back into a loop and pop off the last inserted vertex, which happens to be vertex 1. This vertex has never been visited before, so we now visit this vertex and mark it. This is the second vertex in our order. Now as before, we go through the neighbors of vertex 1. Vertex 0 has already been visited, so we don't insert it into our stack, but since vertex 3 has never been seen before, we'll put it in our stack. Notice that vertex 3 shows up multiple times in the stack, but that's okay. The marking of vertices ensures that they won't be visited multiple times. The next vertex we pop off is vertex 3, which we then visit, mark, and add to the order as the third vertex. Vertex 3 has 4 neighbors, but only neighbors 2 and 4 have not been visited before, so these are the next 2 nodes we add to the stack. After adding these nodes to the stack, the next vertex we pop off is vertex 4, which means it's now the 4th vertex in our DFS order. Vertex 4 has only one neighbor in vertex 3, but since that vertex has already been visited, we do not need to add it to the stack. The stack is still non-empty, so the next vertex we take out is vertex 2. This vertex hasn't been visited yet, so we visit, mark, and add the vertex to our order. We've now visited all the vertices of the graph, but there are still 2 vertices in the stack. The algorithm will not add any more vertices to the stack and will eventually pop off the remaining vertices from the stack, but not visit them since they've already been marked. The algorithm will then terminate when the stack is eventually empty. While this algorithm is a little lengthier and more involved than the recursive implementation, using the stack in this manner is a really helpful way for you to organize information if you ever need to identify the DFS order of a graph by hand on a written test or exam. So you've seen 2 implementations of DFS thus far, and I want to make an important note that for all practical applications, both these implementations are equivalent in the sense that they both run in the same running time of O of v plus e time, where v is the number of vertices in your graph and e is the number of edges. As a result, from a performance perspective, if you run either of these algorithms on a huge graph, you'll see no noticeable difference. However, the reason I want to show you both versions is that the recursive implementation is the more standard implementation of DFS you'll encounter since it's cleaner and easier to read. But at the same time, including the iterative approach is important since it's more generalizable to other graph traversal algorithms that require an iterative approach. You'll end up seeing this logical structure a lot in other graph algorithms, so I think it's a good idea to introduce it here. On the topic of comparisons, let's make a quick note about the differences between a pre-order and post-order DFS traversal. The orders we have looked at thus far are all pre-order DFS traversals. All this means is that we output a vertex as part of the order as soon as we encounter a new vertex. A post-order traversal is slightly different in that we're going to output the vertex as part of the post-order only after there is nowhere else to explore from that vertex. For example, in this graph, the first vertex in our DFS post-order is 2 since that was the first vertex where we hit a dead end and had to go back. The next vertex where this happens is vertex 6, which then ends up being the second vertex in our post-order traversal. And eventually we reach another dead end at vertex 9, which then becomes the third vertex in our post-order. Now vertex 8 is also a dead end, so we can add that to the post-order. The previous vertex 7 is now also a dead end, and this continues until we get to the starting vertex. Here's what the rest of the post-order traversal looks like. And as with pre-order traversals, there are several other valid post-order traversals for this graph. The important idea here is to make sure you understand that a DFS post-order will only add a vertex to the order when there are no more neighbors to explore at that vertex. Implementing a post-order DFS traversal is actually quite easy once we have a pre-order implementation. This is what the recursive pre-order implementation of DFS looks like that we just went through. To make it a post-order implementation, all we have to do is instead of visiting a vertex as soon as we encounter a new vertex, we will now visit a vertex only after all its neighbors have been visited. This idea is reflected by just moving the call to the visit function to the very end of the DFS post-order function. And that's all there is to DFS post-order. In the last part of this video, I want to talk about some of the applications of DFS. DFS with some additional modifications can solve a ton of interesting problems in graph theory. One example is cycle detection. This problem can be solved by applying DFS with the additional check that anytime you encounter a new edge that points to an already visited vertex, you have a cycle. Another example is finding connected components of a graph, which just requires running DFS multiple times. The main idea behind finding connected components is to start by running DFS on a random vertex. DFS will then find one component. The next step is to then run DFS on an unvisited vertex, which will output another connected component. Continuing this until every vertex is visited will give you all connected components of a graph. Another more involved application of DFS involves finding a topological sort of a graph. This feature applies to specifically directed acyclic graphs. Imagine each vertex in this graph represents a task. If an edge points from vertex 0 to vertex 1 as it does here, what that means is that task 0 must be done before task 1. A topological sort basically answers the question of how we can find a valid order to execute tasks in a directed acyclic graph. This particular graph has several topological sorts, one of which is to start with task 0, which allows us to execute task 1 and task 4. From here, we can move on to task 3 and then task 5. From task 5, it's important to note that we can't actually execute task 8 until we finish task 7. So we execute task 7, which now unlocks task 8 and task 9. After this, we can go back and complete task 6 and task 2. Again, this is just one possible ordering. There are several other valid topological sorts. This problem can actually easily be solved with depth first search, specifically a DFS post-order traversal with a few modifications. A DFS post-order on this graph will give you the following as one possible output. Do you notice anything interesting? The key idea is that reversing the post-order traversal of a graph will always give you a valid topological sort of the graph, and I encourage you to think about why this trick works. There's a fairly intuitive justification for why this works that I'll leave to you as some food for thought. The last application I want to talk about is kind of just a fun one that I learned about while doing some research and exploration for this video. Turns out that you can easily generate some really cool mazes with DFS. Most mazes have a grid as a foundation, which we can easily represent as a graph. Now, with this graph representation, we can run a modified version of DFS from a particular starting point, such as the top left corner, and check out what happens. What's really cool about this is that the only difference here is that instead of inserting neighbor nodes one at a time in a particular predefined order, we take the set of neighbors of a node and randomly insert them into a stack. When I generated this animation, it was just a couple of lines in difference from the bare bones DFS algorithm. And it really does generate a difficult and beautiful maze. I had a hard time solving it without cheating, so good luck for those of you who want to try. That's all for this video, and thanks for watching. If you enjoyed the content, please hit the like button so that this content will be recommended to more people. If you want to see more content like this, please don't forget to hit the subscribe button. And if you want to more directly support the work of this channel, please check out the Patreon page linked in the description below. I'll see you all in the next video.